So last week, we talked about a technique to trace memory leaks in your code by overriding the operator new and operator delete. I showed you how you can use that combined with some macro magic that would replace your new statements with a custom new operator and logged in file, line number, and so on of this allocation. And actually, really briefly, let me mention that there is another similar technique that is simpler. Let's see, where was it? New, I think I called it new ST. New trace, and new trace ST. Where is it? Do I not have it in the solution? I thought I did. There we go. New trace and new trace ST. So another way to do this, and even though this implementation creates this macro, it no longer needs it, because here, excuse me, this operator new, which is the main override, falls back onto this macro makes it use this one first, which then falls back onto this one. But this one here, even though it takes the file, function, and line as parameters, it doesn't need it because internally it uses boost stack trace. So whenever it is called, it will first say, hey, what is the stack trace that led me to this call? And it will record this and store this information. So since we learned last week that since C++ 11 or 14, all the other new operators will eventually fall back onto this one, we could greatly reduce this new tracing implementation if we didn't care for file name, function, and line number, and instead, if we had a stack trace that led to this allocation, then all you would need to do is override this operator new and the corresponding operator delete, and that would be enough. Because even operator delete is a fallback for all other operators, all other delete operators, even the array ones or custom ones, whatever, it doesn't matter. They will now always converge onto a single delete and a single new. So that's just something I wanted to mention. The whole thing could have been implemented as a one operator, and then some helper code to keep track of stack traces. I have this on my GitHub, by the way. So if you want to look at this code, you can. Let's see. If you want to look at this code, you can always go to github.com/moi/blog, and here under source are the most up-to-date versions of all my code, all my classes, and from my posts. So here, new trace ST. You can find it here if you're interested. Okay. Back to topic. So again, we talked about this new and delete technique, and I wanted to kind of follow in those footsteps to another similar idea, and that is overriding a new and delete the allocations for a specific type, not globally, right? Overriding the global operator new and delete is a pretty heavy-handed approach because it will be the new allocation method for every call in your code. And from what we saw last week, it seemed like even the code that was linked to the program was then falling back onto it. So if you define the operator new, the standard one that just takes a sizes parameter, all you got to do is include it in your project in one file, and it looks like the linker will then go ahead and replace it everywhere else. At least that is what I have noticed when tweaking that. So, but anyway, what if you wanted to have a type? Let's call it type T. Well, let's call it type P. You'll see why in a second. And when creating instances of type P, let's benchmark it maybe. let's say the type P will hold an int, some value. Let's go into a crazy loop where we'll allocate millions of those. So I equals 0 to I less than, let's say, we'll do 10 million. By the way, these little ticks here, it's also something in modern C++ helps you read big numbers more clearly. You don't have to count zeros, you just look at the ticks and see what's going on. Okay, so here, let's define, I'm going to make it volatile. I'm not sure if I have to, but I will. This should prevent the compiler from eliminating this code. Yes?
Are the ticks standard on C++, or that's something compiler related?
No, that's this syntax of this, the way I wrote 10 million.
Yeah.
Right? You can do this, which is a pain in the butt to read, but you can do, yeah, this is now standard C++. As long as you're doing C++ 11, yeah.
Okay.
Then let's see, what is this thing complaining about? Expected bill after no for maybe it's just stupid intelligence. Okay, so P equals new P. Let's actually pull in standard lib and generate some random numbers. CSTD lib, there we go. So now we can do seed the random by using time, was it? With null. There. That will take the current time and integer form and seed the random number generator, which you shouldn't really use. It's old and it's insecure. I have another blog post and example code. It's right here about better random number generators that you should really be using. It's a little more code, but it's a far better generator to use. Anyway, so let's allocate something. This P, let's give it some random value for this MB. Let's then maybe try to access it. What's MB? There we go. What will we do? We'll just increment. And then delete P. Let's see. It should compile. It did. No, it didn't. Wait.
Are the ticks the back ticks or the ticks?
The left top corner of the keyboard.
Okay.
Yes, I don't. It's not on the same key as double quote.
Yeah, it's the back tick.
At least.
Okay.
Oh, wait. You know what? Maybe I'm wrong. Maybe it's this. Yeah, I was wrong. Yeah, it's the single quote on the double quote key next to the enter on my keyboard.
Okay. Thanks.
Yep. Okay, so this compiled now. Let's run it. Let's see. I should probably put some timing code in here too. See how long it takes. Increment object to volatile qualifier type is deprecated. Yeah, that's right. The volatile keyword is going away. It's deprecated in C++ 20, and it's gonna go away after that. So let's see what happens. Thread 1, main, yes. Did it stop? Oh, I had a breakpoint here. Never mind. Let's keep going. All right, well, that finished fairly quickly. Let's see if we can time it. Here, random test. I think I had no. I had some simple timing code somewhere. Let's see. Here in sorting. There, so let's bring in chrono. Let's see how long it takes, because what I will talk about is overriding the new and delete operator for this specific type, and then finally we will use a pull allocator from Boost, which should make this code much faster. But first, let's see. Start time. So we can see how fast this thing runs. And there. Start time. Where are you? Okay, start time, and then there. This should print something sensible, hopefully. And then end time. Skip this. High resolution clock. There, that should keep it happy. Failed. Okay. What am I doing wrong? Use of separate. Okay, that's right. We need I/O manipulators for this. You know, that's why in my project I created this I.hpp, which just includes a whole bunch of stuff. But I really don't want to use it left and right, because I like to include only the exact header files that I need for whatever I'm doing. Help you remember where different functions come from. Okay, there we go. So this took less than a second. Let's see if we triple it. There, now it took almost 3 seconds. Okay, so we have a pretty good starting point for gauging how quickly we can allocate small objects. So let's say you have a program that, for whatever reason, needs to allocate millions, billions even, I guess, small objects. And for whatever reason, you need to do it using new. So I need to get a pointer to them and carry them around or something like that. So if we use standard operator new, this is going to be extremely inefficient, because every creation will have to make a system call. Right? We'll have to go to the OS, possibly into the kernel, and say, hey, give me some more memory. So that's not very good if you're concerned about performance. And two, if you have a lot of small object allocation and deallocation going on, it can lead to nasty heap fragmentation. So, sure you all heard about pool allocators, so let me explain what they are and how to use them. So a pool allocator is a mechanism, it's an object, which will make allocations, usually for small objects, much faster by requesting a larger amount of memory from the operating system and then managing it internally. So it will chop it up into small pieces and hand out pointers to these small regions instead of going to the OS and allocating new memory block every time. And the way to do this is, first you need to overwrite the operator new and delete for a given struct or class. And you can do it just like defining a member function. So we know it returns a void star, operator new, std, size t, and there we are. That's our operator new. And similarly, operator delete just takes void star p. Okay. So that was easy. So now we defined operator new and delete for this type p. And let's actually give them some sort of implementation that will fall back on malloc. So here we will allocate this memory using malloc, this many bytes. If p equals null, then we will throw std bad alloc, just like standard operator would. And I think for bad alloc I need std except, I think, or maybe new. I'm not sure. I'm not sure. We'll worry about it later if it doesn't come out. Finally, turn. I can only hit the right keys today. P. There, so just like we did it for the new tracing, let's look at it real quickly. With the new tracer, right, we had operator delete, just like that, and it fell back on our internal implementation. But anyway, we did that. That was the last one in the chain of delete calls. So here we do the same thing, but just for this class or struct, and let's pass it to std free, since we allocated it to malloc. So let's put some breakpoints here and see if we're going to hit this code. And here we are. So in the main function, right here, where we called new p, because we defined this new, it will then use it instead of falling back on the global operator new. And similarly, when we delete it, right, in this statement here and delete, it will fall back on this operator delete. Now let's see, I was right about the fallback for different operators too. So let's, instead of allocating one, let's get an array of those. And if I'm right, and let's delete it properly. If I'm right, it should eventually fall back onto this operator new and delete. If I'm right. It looks like I'm not. Okay. Let's stop this. I think what I'm missing here is this. Let's see if this will be sufficient. And here I will call back, I will return my own p colon operator new n. So here I'm calling an operator just like a regular function call. And let's do the same for delete here. Fall back into p operator delete p. Now here's a curious little thing. This is not a member function, even though it looks like it. It is actually a static member function. There. And these operators, as far as I know, are the only functions that can be defined inside a class, and they are always static without you having to declare them as static. But to prove the point, I can define all of them as static, and the code should still run the same exact way. Yeah. So just something worth knowing. Okay, here we are. So here in this main, we allocated an array. So that led us to our array overload. And then finally we came here. And 40, which is the size, which makes sense since it's a 4-byte int and we are asking for 10 of them. Okay. So now that we have those, let's actually engage both of them. So we will do this. And next, p star, so this was a p, so this will be pa for array, new p, let's say p2. We'll do something here with it, plus pa of the middle one, and delete pa. Let's change this code back to what it should be. Okay, let's reduce the iteration count so it goes a little faster. Let's use these breakpoints. And let's see what happens. Okay, 2 seconds. All right. So what have we done? We allocated a total of 40 million objects. of type P. At each allocation, we had to go into DOS here, step into malloc, right? Very inefficient, or it can be. Let's see if we step into malloc. No, nothing good. I don't have the source symbols for it, I suppose. But you know what would happen. So let's talk about a pool allocator. So now that we have this mechanism for controlling every single allocation of type P, we can now use a different allocation strategy, right? So here is a reference for boost pool allocator. I prepared it because I cannot, for the life of me, remember which header file to include. So I do that up here. Allocators. Da, da, da. Okay, now I think I can find it. So if we now go to include boost pool alloc. There we go. Okay, now we'll do. So what we can do now, we could define a global pool allocator, or let's create a single static one for this type P. And
Marty, are you sure that you're including the proper header?
Yeah, I think so. Let's see, pool alloc. Let's see, maybe I need to also include boost pool, maybe just pool, or maybe let's see, object pool. What happens now? Object pool of int. Okay, well now it worked. Cool. P, come on, work. Yes, good call, Jose. Thank you.
No problem.
Okay. Yeah, I was instantiating this thing incorrectly. Okay, back to class. After we spent 5 minutes Googling for how to use boost pools. All right, so what we have now, this struct P has a private static object pool, which it will now fall onto for its allocation. So now instead of doing malloc, actually let's run it one more time and time it with the same number of iterations. Here we are. Okay, so that, doing these 10 million iterations, 40 million objects allocated, takes 2 seconds. Try it again. Yep, about 2 seconds. Okay. So let's now replace this code with our K pool. Dot, and what is the interface here? Malloc is probably what we want to do. There, it will return a pointer to element type, it will be P. So let's malloc, and it already has the size, so we don't need to pass it any parameters, I don't think. Yeah, there's no parameters to this. Because we instantiated in this object pool with type P, so it already knows what size of P is. Okay? All we need to do is return, and I believe this function, but let's look it up just in case. Boost object pool. This should throw bad alloc. Here, malloc function, description, the type of object. Non-throwing destructor, yes. Non-throwing destructor, of course, important. And public members, malloc allocates memory that can, if out of memory, returns 0. Okay, good to know. So we have to keep the code we had there before that checked. So let's take this. Let's revert this change here. So now instead of using malloc here, we'll fall back onto the pool. And in the delete operator, we will free this memory. So pull, free, and pointer to element. Let's see. Are we still building? No. Okay, looks like we need to cast this pointer. P star. There we go. Now it's captured. Looks like it has stricter requirements on signature. Like malloc, pull returns a pointer to P, not a pointer to void. So okay, let's do this, and let's break here again and see if we are hitting this code.
Martin, I noticed that even though the malloc for the pull object know the size of the object, we still are keeping the same signature for the operator new and passing the size even though we're not using it.
That's correct. Yeah, in this here, this size is not used. So in fact, I can just do this, so we don't have an unused variable warning. No, I can't. I have to forward it to right. I have to forward it to this one. Let's keep it. Let's see what it is. So here again, we're breaking. We're doing a single allocation. We're breaking here. And then when we do a delete, right? Where's the line? There we are. Let's go again. And again, we're going to break into this because we're forwarding from array. Good. And finally, array delete. Okay. Good. So now let's time it. And let's hope I don't embarrass myself and this actually runs faster, which it should. But even if it doesn't, it's still a good technique if you want to allocate memory differently. Okay, look at that. 1.4 seconds. Yes. Let's try it again. 1.4. 1.4. Yeah, okay, so it's consistent. So let's now comment this out.
That's about 25% faster. That's actually significant.
Yeah, and we may be able to do even better if we maybe tell this object pool to pre-allocate some more memory. We'll see. Now if I run it without, yeah, 1.9. So there is a noticeable difference for sure. And just to be sure, let's crank it up. That should run for about 10 seconds now. So let's see. Good time for a coffee break. There we go. Yeah, about 10 seconds. Well, 9.5. Okay. And now if we use the pool allocator again, should be about 6-7 seconds.
Yeah, it should be like 6,500 milliseconds or so.
Yep, we're pretty close.
Wow. Yep.
Let's try again. And I wonder if doing a release build would make a difference here. Let's check. I can do a release build on this. Let's see if I do LLVM. Here we are. I think I have a play alias, which will build my playground program and run it. I'm not sure if it will build a debug or release build though. Look how quick this was. So it must be, I guess it's building release. Let's see. Am I telling it to run releasing this script? CMake file, what is it? Da-da-da, da-da-da. I'm not sure. Yeah, I don't see release here. I guess it is. I must have configured it with release, but to be sure, let's check my history. Grep CMake and then grep release. There we are. So let's reconfigure it just in case. So we will remove CMake cache from here, and we will do CMake. By the way, if you're not using CMake, you should learn it. It's a pretty awesome build system. So let's see, we're on the right subfolder, LLVM. I'm in the LLVM subfolder as opposed to here, Xcode, in this project, because I'm targeting different different environments. So if you pull my code, you can actually run, once you fetch it, you run MSBC, and it will create a Visual Studio solution path for it, where you can then compile all the block examples. Similarly, my run Xcode script, pretty simple. It just tells CMake, hey, give me an Xcode project file. That's how I can run all these examples inside Xcode instead of going to a text editor somewhere else and having you suffer through me switching between windows all the time. Okay. So it's using the default Apple compiler. That's fine. We know that we are doing a release build now. So let's play. See how fast that runs now. Okay. 0.3 seconds with the pull allocator. Let's now rebuild it with the standard malloc or standard operating. Not sure if I even need this. See if it's here. Okay. So now play again. Oh, look at that. Still going. 10 seconds, 9 seconds. You see the difference?
Wow.
It's
Yeah,
not
that's
25%. Yeah, it's not 25%.
No, it was
anymore.
25% on the debug
release
version,
build.
but not this.
Yes.
That's significant.
That's a lot.
Yes. That's more than significant, I would say. Yeah, so, and all we did, all we had to do for this was just these few lines of code here. Of course, the real trick, the real fun is in the implementation of this pool allocator itself, because there are several pool allocators out there available, open source, and they may even be more efficient than what's in Boost. But the thing with allocators is there's like a general purpose pool allocator, and then there will be allocators targeted specifically for certain size and frequency of allocations. So you could theoretically optimize this even further. Okay, let's run this.
Of course, the pool will actually be a trade-off in the speed against memory, right? Because
I'm sorry, say again?
there will be a trade-off between speed and memory, because with a pool you will be allocating more than you actually need to
Yes.
handle
Well,
the objects faster.
Well, let's see. Let's compare. Let's skip those deletes, because really this pool, the way it's being used, it doesn't really need much memory, right? Because at any given time we're only holding 4 instances or 3 instances at max. Because we allocate 1 and then immediately delete it. Here we allocate 3. So really, this pool can get away with just holding enough memory for 4 times or 3 times the size of P, and then never again go back to the system. But let's see what other methods
Right,
this K pool has.
How many instances are the pool allocating? Do we know that?
Well, we do know, because in our program, right, we allocate how many instances? Here we allocate 1, then here we allocate 3, but we never have more than 3 at any given time, right? That's why I want to get rid of these delete statements here, which will force the pool to likely go and reallocate some more memory, because the number of these objects is going to grow to a large number, and we can trace,
Okay,
we can see how much.
I see.
Yeah, we'll see how much memory it's using. Okay, P. Oh, that's right, this runs.
Martin, we have a hard break at 1 because we have the stand-up.
Okay, that's fine. I'm recording this, so you can always watch it later.
Okay.
Let's see. So here we had this constructor. We'll just initialize this MD with V. Okay, and let's see what else can we do with this K pool. It's have like something like reserve. Let's see, construct. See, so we're using malloc, which just allocates memory, but it also has a construct. So it looks like it would not only give you the memory, but also build the object, construct the object in its inside of it. But I don't think we could use construct in the operator you would define for this class. Let's see what else it has. Okay, size. Set next size. I don't know what that means. So number, let's see what is type construct and more values here. Just overloads for construct, are they? Oof, it's a lot. Well, we can always look it up. So let's see. Objects pool, public member functions. There you go. Malloc, free is from. Okay, nice. So it can even tell you, given a pointer, if this pointer was allocated using this pool allocator. That may come in handy when you have a mix for a given object, right? You may have a case. I don't know why, but maybe you would have a need for objects that sometimes allocate from the pool and sometimes allocate from the system memory. Maybe when you're allocating a single one, you would use a pool allocator, but then when you're allocating an array and it's of certain size or greater, you can say, okay, I don't need to waste memory inside this pool. I can fall back onto a regular system malloc. So let's see what else it has. It's from, okay, construct, object, allocate memory, pool, that's right, and construct already, destroy. So destroy is equivalent to calling the destructor followed by free. Get next size, number of chunks that will be allocated next time we run out of memory, okay? And set next size, set a new number of chunks allocate next time we run out of memory. Now, what is a chunk? How is chunk defined? Chunk. So, okay. Are we using it right? Allocate
I'm assuming that chunk is probably the size of the object. No, in reality, we're allocating more than the size of the object. So any future allocations is actually free. It doesn't have to instantiate memory. So instead of instantiating one object, instantiate, let's say, 10. So the next time it just gives you the next entry into the array of the 10 objects that has been allocated. So it's not really allocating, it's just returning the address of the object.
And it's managing memory. Yeah, but see here it says memory that holds a chunk of type element. I suppose what they mean is it holds one element. Okay, so I think we can safely use malloc and free. All right, so here it will tell us how many, get the size, number of chunks that will be allocated next time we run out of memory. Okay, so let's see what this gives us. So here, when maybe let's call it here. Probably a better place to call it. But if we make this pool public, so before we run it, let's do p Okay, pull, get next size. There we are. See out. And again, apologies that I have to go back to Google and stuff. I don't remember the interface for this.
Yeah, don't worry. I do the same. I don't have memorized everything.
Yeah, but I should have probably prepared, before the class. But it is what it is.
Yeah, exactly.
Okay, so let's run this again using our allocator. And this will now tell us, this will tell us how much memory, so will it allocate next time it runs out of memory. Okay, number of chunks that will be allocated. Okay, let's see. So this, I wonder if this number would change over the runtime of the program. Maybe we should call it, there we go, segfaulted. What did I do? Did it segfault before because I wasn't deleting? Let's see. Let's run it here inside the debugger. Oh, what happened? We requested an array. Came here. Which then came here. That's fine. Ordered malloc. If store not empty, okay, then store malloc. Order malloc need to resize. Okay, so it looks like it didn't fall into need to resize, and then it fell onto what? Simple segregated storage, malloc. It's interesting. All right. I don't know if it's a bug or if I'm doing something wrong here, but I think if we see if it's going to work if we delete instead of just. Okay, yeah, that worked. Okay, so next time it runs out of memory, it's going to allocate 32. I really wanted to allocate more at any given time. Let's
because
see.
That's where it's gaining speed from. It's not allocating just for one. It's assuming that you're going to require more, so it's allocating more than what you need. That's why I was saying that it's a trade-off between speed and memory. Marty, this is very interesting. I would like to talk more about this with you, but I have to do a button run before the meeting, so I have to do I have to disconnect.
Yeah, that's fine.
But
No
thank you
problem.
very much for the class. It was interesting.
Sure. All right, I'll keep recording, so you can come back to it later.
Okay, perfect.
Right.
Thank you. See you later. Bye.
Bye.
Yeah, same here, Martin. I have a meeting coming up. I have to probably start getting ready for it, but this was really cool. I had no idea about this, so I learned something new today. Thank you so much.
Yeah, I'm glad.